Ooh, that's fine, just as long as it keeps going. Just keep going. One page at a time. Turn on, tune in, drop out. Okay, I've got to figure out a cooler one than this. Turn on, tune in, drop out. I'll figure that out. Got some badass music running. Noise canceling dog bowls. I like it. All right, Instagram, Twitter, LinkedIn, Facebook, YouTube. Roboto. Let's see. Let's see. Yes. And yes. Yes. Instagram. I wonder if I can actually make one. Can I make one? Actually, I can add. Oh, we can go meta on this shit right here. Check it out. Get on an Instagram. Instagram. Get the gram while you can, bro. Can, bro. Do 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 do. Oh my goodness. Oh, picture. We don't want a picture. We don't want a whole picture. I just want like, let's do this. What's up? How's it going, Instagram? We got the electronic ghost coming right at you, straight streaming from the Jitsi meeting. We're going to be doing the live stream via Facebook and YouTube, and we got LinkedIn, Twitter, and whatever the hell that is. Anyway, tune in. Linking description. Was that a little over the top? A little lame? Don't care. As long as we're doing the thing, then that's all I care about. All right, so I should be able to see this on my story. All righty then. Cancel. Cancel. For everybody running around causing mayhem and wondering what they're going to do with their lives now that Cerveza 19 is in their life. Take this time to study. Take this time to learn. If you have to be holed up in a room, you may as well enjoy it. Well, shit, nobody's here. So if nobody's watching, I have snacks. And yeah, watch this. I'll take 2 of these and then everybody will show. I should just start doing this and figuring out how to. So if I can figure out how to teach this, and then we're going to teach this, create the schematics, create the PC, order said PCB, and then we'll teach it again. We'll teach it again. That's my screen over there. Screen 1, screen 2. We'll teach it again with soldering. Oh yeah, That's I love that soup. Soup. Soupy soup. So soup. Man. Oop. Me. Yay. Yay. Take out the trash, yes. Welcome to Noisebridge. Noisebridge is a duocracy. If you want something done, you do it. And the only rule about Noisebridge is be excellent to each other. We are not enabling desktop notifications because I have shit to do. This is not gonna no, thank you. No, thank you. Thank you very much. So very much. All right, watch. See my capacitor? Watch my capacitor spin. Yeah, but what's negative and what's positive? This is, what the hell, bro? All right, 1UF, name, capacitor. Look at that. There we go. So what we want is we want pin number 2, pin number 3, ground. Positive, negative. Oh, whoops. That is not going to work. Can we flip it? Redo, rotate. How's that? Positive, negative. I don't know if this is going to work. This is annoying as hell. Because the positive needs to go here on the trigger, and the negative needs to go here on the ground. And it just looks horrible. Okay. I guess if we have to, we have to. So let's get rid of this. Positive 5 volts to shit. We also need one from 2. To 6. 1, 2, 3, 4, 5, 6. Okay, from 2 to 6. This one is going to ground. See why this is confusing as all hell. Like, look at this cluster duck of freaking wire. This is horrible. And cathode needs to go all the way to ground as well. Hey! Oh, we blew it up. Damn it. What is this? Name, standard, USB standard A. This is 100K. This is 1K. This is 1K. Now, why the hell is this thing blowing up? This does not make sense. Facebook, Facebook, Facebook. 19 hours ago. Abecos. Edit page. This one. Yep. Woot woot. All right. Abecos people. Abecos. Abecos education. The greatest education you could hope for. Something like that. Think of something cool. Pretend I said it. Deal with it. Oh man, I love this. Got my tunes. Got the educations. Just need the peeps. Where my peeps at? Input, actually. This might not be. Oh, shit. Whatever. Let's do battery. 9 volt? Yeah, we can take a 9 volt. We can handle a 9 volt. All right, positive. Positive goes from there to there. Pretty sure it's 1 UF. Volt rating. 1K, 100K, 1K. Pin 2 to pin 6. That's going to ground. Oh, shit. Okay. Wrong one. My bad. So this wire actually just goes from here could have sworn it's just That doesn't make sense. Should it? No, I don't think so. It's the incorrect version. Do not do that. It's bad for whatever the hell they think it is. So positive here for negative goes to ground. Ground goes to ground. Okay. Signal comes out through the LED to ground. Power in, 9 volts, goes to let's make sure this is connected just in case. Hello. Hello.
Hey, Robert.
There we go. Okay. It's like 7 different settings to choose from. Like, I've got the freaking mute on here, and then like the actual connection, and then the freaking connection on here, and then. How you doing, man?
How you doing?
I am listening to music and chilling, getting high, and playing with Tinkercad.
Okay. This is my first Circuit Hacking Monday.
Woo! Welcome to Circuit Hacking Monday. So, Circuit Hacking Monday is Noise Bridge. Noise Bridge happens wherever you decide to make it happen, and it's online now. So, be excellent to everybody. No harassment. The restrooms are in the back to the right.
Right.
Yeah, if you can get there, you can get there. How you doing, man?
All right. No, it's popped in. Glad to see somebody's using this.
Yeah, no, it's this is actually pretty cool. The jiu-jitsu, or like how would you say
Yeah.
it?
Yeah, it works.
Jitsi, yeah.
Did you have any people come in, or?
I had one, but she was just there to help out. And then you.
Okay.
She did reach out to some other folks and let them know that my quote unquote official start time is 20:45, so that people don't feel it. So that people don't feel like they're late.
Oh, right.
And I mean, there is one girl who knows how to get a hold of it, and I think she was just trying to like. She has some other stuff she wants to get done, and then get to the grocery store, and then like. I usually have people come in at about 8 or 9 o'clock sometimes. But I think if I just start doing this more regularly,
yeah, people might show up. I think we're going to try to do a free code camp as well. So
yeah,
are you still going to go out and with the lift bikes tomorrow? Or you don't know?
Oh yeah, I'll be there. So it's actually
sweet.
I was talking to somebody and they said yes, it is a necessity. Whatever the word is.
Yeah, facility or whatever. Yeah.
Right, because so instead of taking public transit, you jump on a bike. You're not crowded with a whole bunch of other people.
Nice.
So we'll see if that actually comes true, because our ridership has actually been down.
Well, yeah, you guys like doubled the prices or something on those.
That too. Yeah. It's not great timing.
Yeah.
If Lyft were to rate like just completely go back to original pricing, and then like whenever this freaking epidemic is over, they slowly get back to the pricing, nobody would like complain. Everybody would be like, "Oh my God, Lyft is so awesome! They're saving the world." And like,
they should probably roll back. Yeah.
Which I kind of hope they would, just because like so many people are pissed about the pricing. Like I canceled my account.
Oh, did you? Oh,
yeah.
Wow.
Yeah. Well, even as an employee, like, oh yeah, well, it's $15 a month, but like that's only for the shitty classic bikes.
Yeah, that don't have batteries.
Exactly.
Yeah, like I took one ride. I think it was like $7 somehow because I parked in the wrong place or something. It's just like no.
Yeah, no, I actually did the calculations, and basically, it came out to about $140 a month.
Wow.
And that was just 20 minutes in the morning and 20 minutes in the evening,
right? Exactly.
To go to work.
Yeah,
that's it. There was no like free playtime or anything in there at all. Like,
and
that's just like, and I live close enough to walk to work, so
yeah. I hear you. All right, I'm probably gonna pop out and go back to answering messages.
Yeah, it's all good, man. Take your time, have fun. Play with Tinkercad. So here's the cool thing. You want to see something cool?
Sure.
Really
what is
quick?
this? What is this? How do I get to this screen?
So you go to tinkercad.com.
Let me try it.
Yeah.
We actually figured out how to project your computer screen Oh, this is pretty cool.
So check this out. So this is an Arduino. See the Arduino round. Okay.
Right.
Now you go up here, and you
Is this
can
actually Italian? Or?
yeah, you can teach in blocks,
Hmm.
or you can go to text, and then you actually have the code which you can then run. And now we're running, and the little L, the LED, if you look really close where the L is.
Mm-hmm. Oh, wow.
This code right here is driving this simulated Arduino. I know, right?
What kind of code is that?
I have no clue. Well, the Arduino is Arduino.
Oh,
Like
okay.
it's a like C variant, C++ variant with like some other junk in there.
What is the L? I don't know. What is the L?
The owl?
The L. The L mean?
Oh, the L. LED.
Ah.
That's the onboard LED on most Arduinos.
Mm.
Is the L, and you can, let's see, digital write 13. 13 is usually Arduino's LED, or you can actually use digital write embedded LED. There's a special word for it that Arduino language knows about, and so whatever board you're using, if you use embedded Arduino LED, it'll just automatically write to whatever that is. It's usually a 13 though. I know, right?
Yeah. I'm getting curious.
It's definitely interesting, and like that's one of the reasons why I thought about, okay, I want to teach this in Tinkercad, just because of like how many different things you can do in here all at once.
Is all free?
Yeah, completely.
Oh.
Yeah, log in. What is it? It's turn on, tune in, and drop out. I'm trying to come up with a better turn on. Oh, I'll come up with something better.
And create a personal account. Sign in with Google. It's really cool.
I know, right?
But wait, so this Arduino is powered by this battery?
I don't know what the back. Actually, let me hit F12 really quick. Let's just.
Oh, Autodesk.
Lame. My computer, my tab just crashed. Crashy tab.
Wait, I see.
I wonder if my tab crashed because I hit F12. I wonder if it can't handle it.
Oh, wow, this is interesting.
I don't know what's running in the background, but it's definitely like.
How can I show you my screen? Because I just got the coin battery, the transistor, and I think the light.
Yeah. Show me your screen. I would love to see it.
I don't know how I do that.
Okay, so if you go to the bottom right-hand corner of your screen,
there we go.
You should see 3 little dots.
Yeah, and then I do.
And then you're gonna go up to. Oh, my bad. I'm sorry. Go to the bottom left-hand side of your screen, where the little
I see.
screen is. And then you should be able to
now you see you. Let's see. So this is where I am. And then, wait, do you see that? Or,
I don't see it yet. Here, let me do this really quick.
Oh wait, I think wait a second. Okay, Chrome tab.
Yep.
Oh, this is actually pretty good. Okay,
I know, right? Look at you go!
Okay.
Now, hit start simulation.
Where's that? This?
Top right.
Oh,
Next code.
man, I messed it up. Stop.
Oh, you broke it.
That's it.
It's okay. Reload it. It's all good.
It's here. And then the light comes on.
Mm-hmm.
Wow.
I know, right?
What is the point of the resistor?
So the resistor, if you think about the Force and the Jedi and Luke Skywalker,
Right.
resistance is futile.
Oh, wait.
So,
I know the connection somehow.
yeah, so literally it just resists. Like right now I have a 3-volt battery. So I've got a 3-volt battery.
Need to go back a lot. There we go.
But if you use a USB like the Arduino, so the Arduino has a USB because you can actually go back.
Oh, that actually have a 9-volt battery you can put in this. Wow.
Right. So you have a 9-volt battery. But if you plug your 9-volt battery directly into your LED, you will blow your LED up.
I see.
So right here I have the 9-volt and a 3-volt. You could actually connect both of these together, which would be interesting. Just for giggles. Like, let me see what it looks like when we blow it up. Like,
yeah, that's what I want to
do. Start simulation. Bam! Oh, look at that.
Wait,
I've got the LED has this like current through LED is 915 milliamps, while absolute maximum is 20 milliamps.
Gotcha.
It actually shows, like, it tells you what's wrong. It's kind of nice.
It's actually incredible.
Yeah. There's a few limitations on spacing as far as like learning how to plug things into a breadboard. But I think if I don't focus on that and simply teach the ideas here, and then we actually go into something like EagleCAD, we could teach like, okay, here's the resistor and how it looks on Tinkercad. Here's how it looks on EagleCAD. Oh, by the way, we printed it out and we ordered like 1,000 of them. So, you know, when you're ready, you can order one with all the parts and solder it at home or solder it at Noise Bridge once we stop dying.
Right. Huh. This is an amazing program.
Yeah, I'm definitely looking forward to seeing how other people use it. And like, is it easy? Is it hard? Like,
it's actually, I mean, I think it was confusing how to delete something, but now I got that. So now oh, crap. Okay, now I have to leave the coin battery. Putting in a 9-volt. Wow, that's huge. Okay, then I want to make a connection, so I'm gonna. Are you seeing my screen or?
No. Show me your screen. See if you can. Bottom left-hand side.
It's more interesting.
Click.
Chrome tab. Okay. So I'm just doing the same thing as you.
Nice.
Is this gonna work?
Well, click on your resistor.
Oh wait. Yeah, it didn't work.
So click on your resistor. There you go.
Yeah.
So you're at 220 ohms. So the other thing you can do is actually, let's see, wow. Ohm's law. So if you type in something simple.
So actually, so the resistor is just modulating the power? Is that?
Right. So the resistor is helping make sure that not so much gets to shit, where is it? Oh, okay, it should be ohm.
Oh, the resistor is actually just a metal series of metal. Not sure.
So let's check this out. So I've got 9 volts. And then, so what I pulled up right here is just simply some random calculator thing that I typed into Google. So I typed in Ohm's law calculator. And so if we say voltage is 9 volts, and if we say current, now when you, for these calculators, current can be anything. But if you look at the battery itself, not on here, but a real one, you may or may not be able to see what it'll say is like 9,000 mAh. That's milliamp hours. So current is in milliamps, right? So if you have current in milliamps, how many milliamps of current can you have per hour? So that's milliamp hours. But for the calculator, what we actually want to determine is based on the 9 volts, for the 20 milliamps of current that the LED is allowed, so we actually need to change this, milliamps, what is our resistance? So if we don't need to fill that in, look at that. So 450 ohms. So if we go back to, so change your resistor to 450 ohms.
Actually, the way it was, it didn't blow up.
Yeah, it might. It didn't blow up. Hey. Yeah. Well, so 270 will work too.
Oh wait, it blew up once I.
Ooh. Well, that was. I think it went to 0 at that point. Yeah.
All right. Well, actually, 220 works somehow. What's any resistance? I know. Looks like minimum resistance is.
It's got to be like what, 150, something like that.
No, it's 660 works. Oh, but that's because it's ohms, not milliohms. So if it's milliohms, that's probably your. What does your screen say?
That's actually mega ohms. Or wait, no, that's milliohms.
Yeah.
That's interesting.
Your screen.
Oh, look at that! It goes all the way. Pico ohms, nano, micro, milli, regular, kilo ohms. I wonder. That's 7. If we go back to the calculator and we actually type in current, so get rid of that. We type in 150 ohms, 60 milliamps. It's a lot of amps. Now I'm super curious. Like, I wonder what the, like, because I know there's, the LEDs can only take a certain amount of power of electricity. But I'm super curious what.
I like how you're rebuilding my weird little circuit.
Like, just super duper simple. Okay, you're on. You're at 9 volts. Oh, that's why. Oh, look at that. Interesting. So, can you see mine?
Yeah, I'm seeing what you're saying.
Okay, so this one, so it doesn't explode, but it does give me the current through the LED is 44 milliamps. Well, the recommended is yada, yada, yada. The usable lifetime of the LED will be reduced. And this is at 150. So at 150, let's go 100. 160.
Well, I got it to 60, yeah. 60, it still works.
Yeah, it works at 55 too. Actually, yeah, I guess it would.
I guess it's just like any amount of ohm almost is like enough.
Well, 20, it blows up. 30, 40, 50, 55, 50, 55. Ooh, okay, so 55. Let's do 50, 53. 53, 52, 51. Oh, okay, so 50, 51. So 50 is the minimum. 51 gives me 119 milliamps. So let me go back to the calculator.
I see how you're seeing that now.
51 ohms.
I'm getting
9 volts.
103 milliamps through the LED.
Yeah, I'm getting 176 milliamps on the calculator. I wonder what the difference is. Like, because even at 50, it's 180. Doesn't make any sense. 119 recommended. I wonder if they're using a. Huh.
I'm putting in a push button now.
That's awesome.
Yeah, this is really fun.
51 ohms.
It's not working.
9 volts. Oh, your push button?
Yeah. Probably need to.
So your push button, if you look at, so hover over the terminals.
Okay, hold on a second.
So terminal 1A, 2A, 1B, 2B.
All right, okay. So I need to kind of complete the circuit, right?
Exactly. Hey, there we go. I like it. Where is...
There we go. And 1B.
Who's that? Oh, okay. Got some LinkedIn messages. I'm like, if it's not about Circuit Hacking Monday.
All right. I'm actually just trying to complete the switch. Let's see. There.
No, see, this is actually kind of cool. This is good.
But it's actually not.
Not too hard, but it's interesting enough to play with.
Yeah, I like the Tinkercad, but my switch is not working.
So let's look at your switch. You have positive and negative voltages going in one side and out the other. So hover over the bottom left terminal.
1 second here. Let's see.
Yep.
You mean this one?
Yep. No. So the button, the bottom left terminal of the button.
Okay.
Hover over it until it lights up.
1A.
There you go.
Yeah.
What does it say?
1A.
1A. Okay, move to the right.
2A.
Okay, go up.
2B.
Yep. Left.
And 1B.
So I think the B's are connected and the A's are connected.
Oh.
So turn your switch 90 degrees.
Yeah. Let me see if I can. Ah.
Yeah, so if you click on the line itself and then press the backspace key.
Okay.
There you
go. That's what I want to do.
Cool.
Delete all those. Yeah, good stuff. How can I turn this though? Or probably just change the connections, right?
Yeah, you can actually click and then press R to rotate. You rotate the part.
Press R.
Mm-hmm.
Oh,
There
there we
you
go. Oh.
Nice.
Yeah. So good. So I want to get
Positive energy through the resistor, through a switch. Now the switch is just whether it's off or on. So, you know, it's all good. There you go.
I'm not sure how I want to connect it now.
That's okay. So, yeah, just stay on one side for right now, which is what you're doing. So positive to there.
So the negative.
And then the top one to the resistor. No. Delete that. And then that top one. Nope. Go ahead and delete that line. You're going to make a line from the right top button post to the resistor.
What's the right top button? This? Oh, I see.
That one, yeah. But that one, yeah, goes to the resistor.
To the resistor, okay, interesting. Like that, right?
Yeah. Now, if you have positive energy going through a button, it's still positive when it comes out. It's positive when it goes through the resistor. When it gets to the LED, the positive energy is quote unquote used, and now it becomes a negative terminal. And now the negative terminal goes back to the negative terminal directly. Don't go back through the button.
Oh. Just like that?
Mm-hmm. Press run simulation and then see if you can press the button.
Oh,
yeah.
Cool. I see. Interesting.
So what's happening is the electricity, you have to think of it like a circle. You have a kind of like a infinity sign, but it's still a circle. Like you're still going out you're still going out the start gate, you're going around the track, and you're coming back to the start gate. So if you follow the line, it goes out one direction, goes and does something, comes back.
I don't see why I don't need to use the other half of the switch, though.
So what you can do is you actually can try putting another LED on the other side.
Oh.
So if you click on the LED, if you see mine, you click on the LED and then you Control V or Control C, Control V.
Ah, I see.
And now you have a duplicate part.
Yeah.
And now I'm going to take this LED. I'm going to put it over here. So if I have positive power coming, now this is a little bit weird just because 1A to 2A is a connection and 1B to 2B is a connection, but 1A to 2B is also a connection. It's just a little weird. These are single pole, single throw. Actually, it's a DPST. So yeah, double pole, single throw, which means that there's 4 contacts, but only 1 control. See, check this out.
Yep.
Now, if I actually put in another one, oh, right, I gotta stop the simulation. Let me lower this. Okay, so we're gonna make another one. Now watch what happens with this pin. Back to negative. So positive energy out. We have a single point of reference for positive energy. Positive energy is now distributed to all 3 of these pins. Now this one, on the other hand, should be on. Yep, check it out. So we have the top, or terminal 1B is always on. And you have these 2 are always off, but watch what happens when I push the button. Oh, shit. I think it was, that one actually turned. It's supposed to turn off, or maybe, oh, no. So mine's rotated 90 degrees, so I think it might actually work correctly if I did it that way. But actually, look at what happens, though. Check it out. So you see how this LED is at 45 milliamps, maximum is 20, and it's got the little exclamation point?
Yeah.
Okay, so when I push the button, the exclamation point goes away. So the reason for that is because the current that is too much for one LED is now split up between 3 LEDs, and it can handle the current.
I see. But it's not exploding.
Right, no, we took it and like changed this to, 10. Now it's exploding, and these would explode too. So go ahead and try it. See if you can get
I don't actually get why the switch has 4 pins. I don't know why that switch has the extra pins.
Right. So the reason it has those extra pins is inside of electronic circuits. You usually have, it's not just electricity 5 volts or 3 volts going through a button directly into an input on a microcontroller. What you actually have is the opportunity to say, pull down or pull up the input without adding extra components or connections. That's one way of doing it.
Mine didn't work. What's anode versus cathode?
Step by step. So let's see, where are we here? Okay, 2A, 2B, 1A, 1B. So let me align this. Okay, from 1A to 1B, I should have a regular. No, it's not. Interesting. Right, actually, I think it was. Wasn't it reversed? Okay, here we go. There we go. So if you're there, that should work. So 60, let's just not blowing up on us. But then this one. So
I'm not getting any light.
tactile switch. DigiKey. Let me see yours. Okay, so you've got 1, 2, 3. Crunch. Okay. Positive. So why don't you go back to 2 LEDs first? So one of the problems with adding too many components all at once is that you actually have to keep track of all the lines. And this goes for the same on hardware. When you're actually touching the breadboard and you're like wiring this thing up, especially if you're like trying something out for the first time, you're like, oh, let me just try this. Start with one piece and then add 2 pieces and then make sure that works. And then once that works, add a 3rd piece.
Okay, that makes sense. Let me see. No. Okay, that works.
So at this point, what I would recommend is actually moving your resistor between the positive connection of the 9-volt battery and the button, because
Okay.
you want to limit the current for all of the LEDs, right?
Oh, I see what's happened.
Because right now you'll just be doing one.
Yeah, that makes sense. I didn't think about that. But wait.
So go ahead and delete the line that's going from positive 9 volts to the button.
I'll move it.
Yeah, click and then backspace.
Ah,
It's okay. Click,
Yeah.
backspace. There you go. Now delete the line that's connected to the resistor. Okay. Move that thing down. Press R to rotate it so it's in. Yep, perfect. Bring it down a little bit so you give yourself some space. Perfect.
yeah. So all positive current goes through that.
Mm-hmm. Because now you're controlling the current for all
Yeah.
3 of these LEDs.
Go to the switch.
And now turn your LED. Well, actually, you can't. Never mind. So connect one LED first.
See. I want to move this one. Why won't you move?
You can do it.
All right, fine, whatever. I'll just do this one first.
So go ahead and stop. Look at what you're connecting. What are you connecting?
Cathode. Oh, cathode is out, right?
Yep. There you go.
Kind of an
And
ugly.
then start
Yeah.
simulation. There you go. Push that button. Cool. It lights up. We're going to blow it up, but that's fine. It lights up. That's what we care about. So now connect. Do the exact same thing. Hold on. Stop, 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 stop. There you go. So do the exact same thing, but for a different connection. Ground to ground. Perfect. Press start simulation. Let's see what happens.
Nice.
They both turn on. Okay.
Wonder if Now, why do you say this exclamation mark? Current really is.
It's just an overcurrent.
Okay.
It's not enough to necessarily, quote unquote, blow it up. but it will degrade the LED.
I see.
And so like right now, if you look at my screen, I'm looking up LEDs. And these are actually called tactile switches. So if you say, okay, I know what to call the switch. I know what to call a tactile switch. Let me add on the end of that data sheet PDF. You should get at least, oh, look at this. This is nice. This makes it super easy. This is most of the tactile push buttons. Internally connected. So if you look at the switch, it's actually connecting pins 1 and 2 with 3 and 4. But pins 1 and 2 are already connected. But this means that if you go and you actually create an input, so you keep working. I'm gonna see if I can set this up for you on my side, so I can show you something.
I don't get why the third LED is always on, actually.
So go back to this one. Look at the top right picture.
Mm-hmm.
So
it's internally connected, I see.
Right. So if you're connected on the top left, if your power is connected on the top left, it's going to naturally flow out the top right.
The switch doesn't matter anymore. Yeah, I see. Okay.
You go there, and you go there. 50 ohms, saturation. Cool. So what we want. Actually, I should show you the MOSFET. That would complicate things. Actually, so if you check out my connections right now, I have 2 lines coming out of the positive end of the terminal of the battery, going to 1B and 1A.
Yeah.
And then 2A and 2B are connected to the single resistor here. And if we close the circuit, start the simulation, it works like a switch.
Okay. Yeah, so you're saying.
Now, if we do this. Oh, right. Okay, let's do that. So what I'm going to make is called a pull-down resistor. So this is important when you're working with Arduinos, because if you have a floating pin, it's not a 1 or a 0 for an input on the microcontroller. And the reason it's a floating pin is electricity kind of just can sit on a pin. It kind of moves around. And if you have electromagnetic forces in the room that are strong enough, it can actually send electricity along that piece of wire when you didn't really mean it to have electricity.
Right.
So what you do is you actually take something like this. So the resistor that I'm playing with right now, we would actually have it 1 mega ohm. So if you look at the path, we're taking anything that's we're gonna take this LED as an input. It's gonna be this is gonna be the pretend input for a microcontroller. Now, if you have this resistor here protecting the microcontroller, that's great. But if any EMF comes along on the wire, it could actually trigger a 1 here instead of a 0. So in order to make sure it stays a logical input 0, not a floating gate, not a floating input pin, not a 1, but we want a true 0. What is true 0 versus a true 1? What's the difference? Do you know?
Yeah,
I do not know.
Yeah, I was going to ask you about microcontroller with that too.
Yeah, it's all good. So a 0 on, let me see if I can actually pull this up. TTL, so transistor logic, and then there's CMOS logic. There's a couple different voltages. That is the wrong one. Anyway, but the idea is 5 volts is like your 1. And there we go. 5 volts is like your 1, and 0 volts is like your 0. And it could be 3 volts as 1, 0 volts as 0. It just depends on which logic you're using, and that's so. If you look at the resistor,
I can go back to that.
yeah. Well, that's a whole bunch. That's a whole bunch. We don't need to do that. There we go. So on that bottom resistor, south of the button, do you see that resistor? So the one you have right now is simply a current blocking. And that's the same one that I have right here. Now, this one is not a current blocking resistor. So this 1 mega ohm, not the 150 ohm that we're protecting the LED with, but I have 100. It's a 1 mega ohm resistor. And this actually it connects to the input here through this, because this is internally connected, through the resistor back to ground. Now, so ground is 0. So logically, that's a 0. The only problem is when we push the button, electricity flows down through the button, and then it can flow here. Like if we just wanted to connect this to ground, now it's grounded. That's definitely a 0. But when we push the button on this, we're actually shorting the battery. So in order to not short the battery, but still get the effect, let me see here. Stay. Okay, it doesn't want to stay. But still get the effect of this resistor, going to force the system to be a 0 instead of a 1 whenever the button is not pushed.
Would you call an LED a microcontroller? It's not really, right?
I mean, there are ones that have extremely tiny microcontrollers in them. They usually blink like a multitude of colors and then maybe some patterns. But no, it's not a microcontroller.
Yeah.
It would be more like it'd be a component.
Right.
A component, a discrete component, a light, a lamp. Depends on how old the person is you're talking to.
So I'm still kind of confused here.
Yeah,
why does it not, even though there's now resistance between the negative and the button, in this scenario, if you push the button, wouldn't it still like technically be shorting the battery even though there's resistance there?
Exactly.
Or is it okay?
Yes, it is shorting the battery.
So in this configuration, it's still shorting the battery.
Yes, okay. But if we go back to Ohm's law,
least resistance.
Well, I can't pull it up. Anyway, I'm just going to pop it in really quick. So 9 volts current. We don't really know what that is. We don't really know what power is. We don't really care. But resistance. So 9 volts plugged into Ohm's law with a resistance of 1 mega ohm gives us a current of 0.01 milliamps, which is very, 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 very small. So that's just the current that's going through. But if we wanted the voltage, I don't know if we could actually get that. So 0.01 resistance power says 10 volts and round it up. That's wattage. Well, the current's the important part. The voltage is pressure, but the current is how much is actually going through at once. Let's just say it's super, super small. Because remember, the LED, the maximum an LED can take is 20. That's 20.0 milliamps. What's going to be leaking from where the button is pushed back through the 1 mega ohm resistor to ground is 0.01 milliamps. So yes, it is leaking, it is shorted, but it's so slow that it's not technically considered a short. Usually when you have a short, it's dangerous because the electrons are actually trying to force themselves down this wire as fast as they can to get back to home. But if you have a resistor in place, they have to slow down.
So you just put a gigantic resistor there? Could you just put like a gigantic resistor there and then no current would go through?
I mean, a brick, I guess. Like, you can, but current will go through it. It'll just be really, really small. Mm-hmm. So like if we put, 100, what is this? 10,000 mega ohms or giga ohms. Okay, let's go. If we're going to go all the way. Right here, 10,000 giga ohms. Yeah, it's definitely not going to let much through. Let me plug this in. Super curious now. 23,000 mega ohms on 9 volts. We don't know what the current is. We don't know what the power is. Mega ohms. So 1, 2, 3, and calculate. I mean, it comes up with 0, but it's probably like 0.0000001 or something insane.
I'm going to try that on my little one as well. Here, I'm going to put a huge.
Yeah, go for it.
Yeah.
And feel free to copy it. Like, one of the things about electronics is that when you start, like, so you have 3 LEDs, so automatically just delete 2 of them. Always go back to the simplest form. And don't worry about like, oh wait, I have to save this because like I need to know how to do it again. That is one way, but if you want to learn faster, it's better to actually destroy it, make something else, come back to it, and have to look it up again. And this is where the 10 hours of research and practice for 1 hour of every like real work that you feel like you're like, oh, I did it. It just takes that much time to go back through and like, you know, go find the web page that has the tutorial on there. Like, why is it doing this? And what do those numbers mean? And actually playing with Ohm's law, writing it out and doing the calculations by hand with a calculator.
It's kind of fun changing these. I get that in programming too. It's like, should I document or should I just rebuild later? But it's kind of interesting changing the ohms because they actually in the simulation they have the LED dim.
Nice.
Yeah.
Yeah, no, we definitely have. There's also an RGB LED in here somewhere too, and some motors and some other cool stuff.
Like the mega ohm itself.
The mega ohm.
Yeah. Once you get to the kilo ohms, there's a difference between 1, 5.
Yep.
Yeah. I thought for some reason that push buttons worked diagonally. Is that?
It
the way these
depends.
work? Okay.
It does. Like, let's try this. Let's see what happens. Start simulation. Okay. Well, let's try. Oh, let's try this. Check that out. That's all sorts of diagonal.
Well, now it should just always be on. Oh.
So this is 1B and 1A, 2A, and 2B. So yeah, these are definitely internally connected. Whereas, actually, here, let me show you. So let's do this. Okay, actually. Okay. Check this out. So
those are always connected.
Yeah, exactly. So 1B and 2, yeah, these two are connected internally, and these two are connected internally.
So if you click it now, will the other one still light up?
Yep.
Did you use the stinker cab before, Tyler?
No, I've never touched it before. It's actually pretty cool.
Oh yeah, it's really cool.
Yeah, I didn't know how cool this was until like I tried it again. And so notice we haven't really touched the breadboard. They do have a breadboard, but honestly, it's kind of annoying.
Usually in Circuit Hacker Mondays, you're going through the breadboard. And,
yes, yes.
The breadboard is basically like you can connect circuits wherever you want, right? So
yeah.
Right.
Because you don't have this really nice instant create a wire and solder it tool.
There's
you had.
Right. Which is nice.
So the problem with the breadboard is if you have a wire, like if you have a component here, right, and you want to control an LED, So if you look at the LED as it is now, the positive side is on the right and the negative side is on the left. I actually want to turn this around, but I can't keep it in the same orientation if I want to do that. Which isn't so bad, but like once you start getting more components on there, it turns into a something.
Yeah. I'm actually going to run through a test with the slide switch.
Oh, nice.
I do like the little zoom. There we go. Okay.
You out there doing stuff on your own. I love it. This is cool.
This says 1, 2 in common. What's that?
The slide switch. Oh, we just blew my LED up. There we go. This one's actually let's do. Let me do this. Now remember, so when you hover over the right, that's how you can see 1, 2 in common, right? So remember, common is literally what each other pin connects to. So if you have a common fork in the road, you're standing in front of the fork, and then you can go left or right.
I don't understand. I lost the tab somehow. Oh, there it is. Okay.
Are you ready for tomorrow, Tyler?
May you sign off.
What's happening tomorrow?
Meeting. The meeting of the century.
I think actually this Jitsu works pretty well. Or Jitsi, I guess. But,
See what you got. Where are you? There you are.
Yeah, the big thing is that Noise Bridge is probably going to need to kind of close its doors.
Just a little bit, yeah.
Just a little bit. And you open Slack, everyone's like, no, we're a public facility. We can use our gaming laptops to fight the virus. Okay, guys, but
no, I mean, like if we took all those computers in the back room and set them up and linked them up, I mean, maybe it could help. But like the idea would be to set shit up and then access it from the outside, so that we're all not there.
Yeah.
Because like I could have the thing right now and nobody would fucking know. Like it would just like, 3 weeks of like 2 to 3 weeks of no symptoms and you're just spreading it all over. It's like, okay, cool. And it's not that much of a problem. It's just the problem is when it comes in contact with people who don't have the immunity or have other issues.
So my basic switch is not working.
Oh my god, did you buy it a latte?
It's totally out of this. None of this.
Zoom in.
Wait, what's that?
Okay, so.
Oh, you need to use the middle wire for your switch.
But why?
It needs to have a ground coming into the switch.
What does common mean? Is it Tutankhamun?
I mean, you know what? I think I still have that super powerful resistor. So I need to. Let me change.
Right. So the top and the bottom pins are terminals 1 and 2, and common is what is connected to both of those terminals. So the common, like common ground, or we have something in common. Yeah, it's pins 1 and 2, or pins 1 and 3.
Oh, so wait. Oh, so it's working when. Oh, so down position's on. Okay.
But then why does it not work when you switch it up? What's happening? What's connected to terminal 2?
Well, nothing's connected right now. Ah!
Woohoo! Actually, Control Z might bring it back. There you go. Cool. So the wire with the resistor on it, try putting that on pin number 2. Now, what did you just put it on?
Common.
Common. So pins 1 and 3 have something in common. What pin is that?
On the middle pen.
Common. There you go.
Yeah.
Now, you're controlling one LED on one side, and I'm pretty sure that'll work. Can you put another LED on the other side?
Let me try with this one. Oh yeah, that works. Okay.
Ah, there you go. Make sure that works first.
To the transistor, goes to the common, switches on.
Did you say transistor?
Go to resistor.
Okay, I was like, wait.
And then goes to the anode, cathode, takes out the. I don't know why my screen is so minimized. The zoom is terrible. Okay, and then.
Oh, you may have pressed control while you were scrolling.
Oh, maybe. And then I want to. So if I want to connect another one, I'll just connect it to the same.
So go ahead and bring that LED down below the resistor. So that way you're not crossing too many lines. No, I'm sorry. The non-connected one.
Okay.
And then delete one of those LEDs for now. Yep, just simplify, always keep it as simple as you can. So now you can take power from what side of the resistor?
This side, right? This side,
Yeah.
Switch.
Yeah. And then which leg is longer if you measure it? There you go.
Well, now the switch is out of the equation, though.
Not yet.
Connect the cathode.
To where?
No, to the switch.
Doesn't make sense to me.
Did you start the simulation?
I thought I started it. Okay. Oh, see, it's only one.
Okay, so well, if you have the switch in the up position, and if you look at the actual switch where the little gray box is, it covers 2 terminals. So when the switch is up, you're covering 2 terminals. When the switch is down, you're covering 2 terminals.
What do you mean by the terminal?
I'll have to actually get a picture of it for you. There.
Right, see how it works.
Let's see.
Probably running the same way.
Cool. Now, can you move one of those LEDs to the other side of the terminal of this switch?
Yeah, probably. I mean, like that maybe.
And the connections as well.
Oh, you don't want to use both connections.
So look at the bottom LED.
One will be lit. One will light up when the other one's on, and so forth.
Exactly. No, that one was good. Put that one back.
This one goes to negative, right?
Mm-hmm. You got it.
This
And positive, why is it going to that bottom pin? Where's the positive energy coming from?
Coming from the resistor.
Coming from the center pin.
Yeah.
Where's the resistor connected?
To positive. I see.
Where else is it?
Oh, so the common one goes to both. Yeah, I got it now. There we go.
Woohoo!
And that the actual
Cool.
tiny piece of switch that you're moving back and forth is effectively just like a copper plate that completes those circuits.
So if you look at my screen on the right-hand side,
It's like an optic. Yeah.
there's literally a piece of metal that touches both pins.
I see.
And then when you move it, it touches pins 2 and 3 instead of 1 and 2.
Hmm.
But that's why pin 2 is called the common, because it's common to pins 1 and 3.
So this switch is not really an on and off switch. This is like a toggle switch.
Well, technically, it's a slide switch. Yeah, there's all sorts of weird little like if you look at this one, like this one has 1, 2, 3, 4, 5, plus on the other side. So there's 10 pins on this thing. So it really depends on what the switch is meant for. Like if it's meant for switching over data or audio or simply an on and off switch. It really just kind of depends on the need.
Mm.
And each switch is a little bit different depending on which one you get. Some of them have designations of a single pull, single throw, or double pull, double throw. And I highly recommend watching a YouTube video on that if you're interested.
I mean, it is interesting.
So we have that.
So
Let's do.
Yeah, I feel like we're at the very surface of circuit hacking.
Let's see what you got. Cool. What do you like about Tinkercad?
Me?
Yep.
I mean, that's easy, I think. Definitely easier than soldering. And you have to get the logic straight, so it reminds me of programming. You are getting down to the logic of circuits.
Yeah.
And it's sort of beautiful in a way. I mean, you can try to design your circuits in a elegant way.
If you're good enough at circuitry, you don't need programming.
Exactly.
Well, yeah.
So that's a lot of circuits.
or circuitry is a kind of programming, I guess.
No, totally. And you can definitely go through I have the transistors here. I was going to go through some of them depending on where everybody was and like. But yeah, there's a bunch of different cool things in here, and we'll be playing with the Arduinos and making cool stuff.
So a longer one is the input, and then the shorter one always goes to negative.
For this exercise, yes. It doesn't always, but it can. If it goes to positive, then there's some route that it might go to negative, but like it just depends on what you're trying to accomplish.
You made a pretty cool.
You got a little blinker.
I'm pretty happy with this.
Nice.
Yeah.
Hey Tyler, you have any questions?
I do not.
All right, it's all good. Enjoy the show.
I'm just enjoying Paul with his new blinker.
His new toy.
For, Tinkercad.
I mean, we could totally make some money off of that.
Yeah, I think that's no. Maybe with the temperature one, but
here you go, Paul. Drag and drop the LED RGB in there.
Ooh.
Up a little bit.
This one, okay.
And delete. Actually, yeah. Delete both of your LEDs. And now, which one's the anode on this one?
This is the cathode, and then there's the
cathode.
So I guess cathode goes to negative, right?
Oh, hey, that's easy. You got that labeled.
And then, and I'll take another leg to another one.
We can do red and green. Ooh. Yes, this is great. No, wait, what would happen? Where would I have to connect the blue one? Probably is.
If you double connect one of them, you'll get a color that's in between.
Oh, really? Try it. Yep.
You could try adding a second slide switch.
Well, or we need a. Yeah. Now how would you do this?
Oh, what's that?
You think we need 2 slide switches?
I mean, you could use 3, but like.
Yeah. If you wanted to make it truly like all color, you would need 3.
Yeah.
Well, technically, we could pull out the Arduino. Oh, this one has an encoder. Okay, that's cool.
So you could take the common off of this one too, and connect it straight to the resistor.
Wait, how do I get?
Yep, you're good. Keep going.
No, I have to get power to the other switch, though, right?
You need to connect it to the connect that resistor to the common of the second switch.
There you go. Ooh.
Now we have a flash on Tasha.
More or less.
Magenta.
But I think I can't get pure red this way. I can get pure blue. I can get pure green, but I can't get pure red. Because I need a third switch for that, right?
Oh, right, because it's always on. Yeah. Totally. Split them up and
this one.
There you go. Perfect.
No, this is like a flashing Toshin. I'll be pure blue, pure red, pure green.
Ooh.
Yep. Underneath this, I know they're just hex codes. Creating the colors, but I really believe that. What makes the colors in these LEDs? Is just the frequencies of the metals or something?
I don't actually remember. It is something to do with frequency, definitely, because different frequencies cause different colors.
Light emitting diodes. Oh, actually, a Wikipedia article has it.
LED. My tab doing. Close some stuff before my tabs crash. Oh, there's a Tyler. Sweet.
What up? Yeah, almost burning food in the oven.
Sweet.
All right, guys. Quarantine starts in an hour and 56 minutes.
Are you serious?
Yeah.
You're not like
it's sheltering
and pulling a virus out of your hat.
Sheltering in place.
Yeah.
Been doing that since I got off of work.
Yeah. Exactly.
Yeah, I'm going with a no shave sheltering this next 3 weeks. So I'm gonna go for a full on beard or whatever scruff I can manage.
I was gonna do that.
You could go no shower sheltering.
Yeah, sanitation.
I mean, like, it would prove that you're sheltering, I guess.
True. Save water for the needy people, I guess.
Yeah. No, it was hilarious reading the paper. It was like, all residents must shelter. And then, like, this is not, what was it? Homeless people do not have to comply.
Yeah. Yeah, no, the announcement was definitely poorly done and not well thought through. So, like, it's quarantine. Everyone has to stay in their homes, and effective tonight. Right. People were like, "Well, what about stores?" And it's like, "Well, stores are still open." Well, what about work? It's like, "Well, you can still go to work if you need to."
Well, then that's like what I think. Yeah.
Can I walk my dog? Oh yeah, that's fine too. It's like, just avoid other people on the sidewalk. It's like, okay. The first announcement was way more panic.
Yeah.
They did not think through the edge cases.
I mean, but there's a lot of edge cases that can be grouped up into, like, are you walking for fun? Well, maybe not, but
like tomorrow I was going to go check the mail. I mean,
you might not be able to do that, Tyler.
Actually, I don't know.
You'll be breaking the law. No, I'll be out working tomorrow. We are considered a necessary, what do you call it? Necessary. Because we're fixing all of the
bikes that people shouldn't be allowed to use.
Well, so if they have to use a bus to go to work because they are necessary for order, or if they work at the grocery store, they have to use transportation to get to said thing. And people are allowed to go and grocery shop. So.
Yep. And bike transportation is safer than bus transportation.
Exactly. Because you can at least, like, wash your hands afterwards, whereas, like, you can't wash your body afterwards, like, every time you get on the bus.
Yeah.
Yeah. So what do you think? We should close Noisebridge or what?
Probably. Tim suggested making physical keys and handing them out.
That's not a bad idea.
And then unplug, huh?
Yeah, just to unplug Noisebridge, literally.
Well, unplugging the access control and making physical keys so that people can still get in.
Yeah.
And just handing them out to people who are going to be actively helping move.
Right, versus, hanging out and working on shit.
Yeah.
Which is not a bad idea, but, like, at the same time, like, we have to start moving. We have to start. And this isn't this isn't a bad time. Like, this is perfect.
Yeah.
Noisebridge is closed because of the virus, not because of us trying to move.
Closed really for both. Like it's
It's
got its ups and downs for sure. But it will be easier to pack things and start moving things without people like hosting events.
Yeah, that's true.
And classes and just trying to go there and hang out, and work on your laptop, play video games, that kind of stuff.
Yeah. No, I agree. It's like, honestly, with Circuit Hacking Monday, I can do Circuit Hacking Monday twice a week on this shit.
Yeah.
It doesn't have to be like hardware in front of you.
I learned something. I learned a lot, actually. Now, I mean, I didn't know about that, but there is such a thing as doping.
Are you worried about doping?
San Francisco drugs.
Doping a semiconductor.
Oh, yeah.
It's phosphorus and aluminum. I think that's the two.
It's the intentional introduction of impurities into an intrinsic semiconductor.
Yeah.
For the purpose of modulating its electrical, optical, and structural properties. I guess that's what's.
It makes it pretty much makes it so current flows in one direction. Inside of, which is or current flows in the same direction that current is applied. And yeah, it's the basis of all modern computing.
So there's actually a 3-hour documentary on the story of electricity. If you type in what electricity, what is, you'll actually be able to find it. I think it has some ads, but it was actually really good.
Okay.
But like literally it's 3 hours, and it goes through a lot of like history and what they tried to do and all this other stuff. Oh, yeah, and then you can actually get into
the cool, the cool pre-transistor transistors, I think, are still awesome.
Oh yeah,
like the glass tube transistors where it becomes conductive when it like heats up and stuff like that.
Yeah,
but it meant that that's one of the reasons the computers were the size of a warehouse, is because you need a million transistors, and each transistor is like the size of a pint glass.
Yeah,
and actually glass.
Yeah, totally.
It's electricity. What is it? Is that the?
Oh, YouTube.
Yeah, I'm on YouTube.
Okay, so yeah, literally type in electricity. What is?
Okay.
And it's going to be story. Actually, let me just.
Oh, story of BBC, right?
Yeah.
Okay.
So I'm going to do it the cool way. All right, I just put a chat message out for you.
I want to know what the inductor does.
Yeah, so the inductor is actually really cool. But you need to understand what a capacitor is before you jump into an inductor.
Ooh, the inductor really blew up the LED.
Nice.
Yeah. Well, I guess.
But the conductor and the capacitor are related as far as what they do. And you actually need to know a little bit more. I would look up this. So there's the idea of electromagnetism and magnets and electricity. That is definitely a video to start with. Once you understand what electricity does in a wire and why it turns into a magnet, at least a little bit, understanding what an inductor does and what a capacitor does will be easier.
Okay. Makes sense. I'm just messing around with this now.
That is the point.
I have a lot of things in here.
All right, guys. I'm going to peace out.
Peace
Good class, Robert. And I've actually never used Tinkercad before. This is pretty cool looking now.
Yeah, give it a shot. And if you don't know, you can actually pull in our Arduino and write code that runs in Tinkercad.
Yeah, Robert was showing me that.
Yeah, that's pretty bitchin'.
That's pretty
It's
cool.
all good. Have a great night. I'll see you tomorrow.
See you tomorrow, guys.
Well, I'll see you tomorrow on some site like this. Or we're going to use Jiu-Jitsu?
See,
I guess.
I was actually looking at the traffic rating, and it's trending really high in Italy right now. So,
Oh, shit.
I guess there
Hey,
was
how many people can we actually host on this thing?
I
Is
don't
there a
know.
limit?
I don't know. I think it's pretty good. So it's just a matter of not everybody chatting at the same time.
True. We're definitely going to have everybody sign in on the little message thing if you want to speak.
Yeah.
And then the other cool thing is I can, like, as the moderator, I think I can actually. Oh yeah, I can do this. Doop. Ha. You can hear me, but I can't hear you. Can you unmute yourself?
I just did, yeah.
Nice. Okay. So this will be the moderator's job to, like, mute everybody and say, hey, we're actually going to be moving on. If you'd like to speak, please put your name in the thing.
I have to keep muting people as they unmute themselves.
Definitely.
Up to 500 people, it says. You muted yourself, Robert.
Nice.
Yeah. You just muted everybody.
Including myself.
Including yourself, yeah. The compiler would like to speak. He's requesting to speak, but
Compiler.
you're not letting him speak.
Oh, what?
He's saying bye. Oh, he said he muted you.
Oh, okay.
Okay, bye, guys.
Right, we're leaving. Yep. All right. We'll see you, Robert.
We'll see you tomorrow.
All right. Yep.
Have fun with this thing.
Thanks for the meetup. Yep.
No problem. Cheers.
Bye.